This video constitutes the third and last portion of the video for Chapter 5 of Introduction to R for Business. Now, picking up where we left off from the second video, let's go ahead and clear out the console, for instance, and let's talk about missing data. Once we start getting things like vectors, and in just a little bit when we start talking about lists and data frames and so forth, we have to be cognizant of how we're going to handle missing data. Now, one way you can handle missing data is you can pass the NA function to R. You can store the NA value. And if you do this, NA actually gets stored, but R knows that that's a not available, right, or not applicable element. So it's in there, and you can look for it. You can say which of the elements of Z are equal to NA, for instance, and it tells you the second and fifth ones are equal to NA. Now, one of the problems, though, with using NA is that some commands, if you try to run them, right, so you can do this. You can say Z cubed, and it will do Z cubed on the elements that it can do the math on. It won't do the Z cubed on the NA values because it has no idea what, if you can't tell it what the second and fifth elements are, it can't tell you what those things cubed are. Now, what this means is if you've got any command that summarizes across elements or rows of a vector, the whole answer is going to be NA. And R is probably doing the right thing here. It's telling you, okay, I know that you've got a 2, a 6, a 8, and a 12. I don't know two of the things you've got, so I can't tell you what the sum is, right? So that sort of makes logical sense. Now, one thing you can do is instead of using NA, you can use null. The problem with using null is that it doesn't show up. It doesn't even get stored. It's basically saying, hey, skip me in the assignment. So rather than winding up with 6 elements being stored in Z, you're only going to have 5 elements stored in Z. And, you know, we could even make it so, let's suppose that we wanted to replace all of these with null. Now we can do our sum command and so forth, right? Oops. Helps if you do that in the right place. And it'll work. The issue, though, is that sometimes you don't want to skip elements. If you're thinking ahead, we've talked about character vectors, we've talked about numeric vectors, we've talked about date vectors. We're about to the point in just a second where we can start talking about, hey, maybe those different vectors can be combined together, and which element number something is in one vector helps us look up element numbers in another vector, right? So let's suppose we had a vector of names, and then we had another vector of weights and ages and birth dates. And we found what element number in the first vector Tom is. We could then say, well, Tom is the 5th element here, and if we stored things consistently, then Tom's age is in the 5th element of the age vector and so forth. That works if you put NAs, right? Even if you don't have the age for Tom, everybody else's ages will line up correctly if you're using NAs. But if you use nulls, you're going to have problems. So whether we use NA or null depends upon sort of, in the end, what we intend to do with the vector. If we want to do math across the elements of the vector, we should use nulls. If we want to use it to look up things and then go and find things in a systematic manner, we'll use NAs. So we'll see when we get to more complicated things at the end of this video, such as data frames, that normally if we have a choice about how to bring in missing values, we want to use NA because we want to use place as a way of locating things. Now, let's go through and talk about sort of some useful commands before we press on. First one is incare. Now, this is, if you were thinking about the len command back in Excel, this is what tells you how long a particular element of a vector is, right? So little n name had 3 names in it, Mike, Lucy, and John. They all happen to have 4 letters. Well, when you run incare on name, it comes back and says the first element has 4 letters, the second one has 4 letters, the third one has 4 letters. So incare tells you how long a particular element in a character vector is. We've already talked about length, right? The x vector has 6 things in it. And we've already talked about mean. The average, or the mean of the x vector, is 6. So let's clean up, and let's talk about arrays and matrices. Now, arrays and matrices are going to generally be combinations of different vectors, but where all the vectors are numeric. You can create an array using the array command. So we're going to pass it 2 bits of information. First, we're going to be lazy and just use this shorthand way of saying the numbers 1 through 9. So what goes in the array is the sort of first argument of the array command. I'm going to put in the numbers 1 through 9. They could be numbers that I get from someplace else, but this is the easiest way of sort of filling out an array. The second argument for the array command is what dimensionality it needs to have. These are going to be the number of rows and columns. Think of this as a table, right? When you run this and it puts values in the array, if you then run the view command, which lets you see what's in a memory storage location as a table, it looks like a 2-dimensional table, right? You've got rows and columns. And sure enough, I've got rows 1, 2, 3, and I've got columns, which it calls V for vector, vector 1, vector 2, and vector 3. Now, this is pretty handy, and if you need to look something up, again, we're going to use our friend square brackets, but inside square brackets, because now we don't just have elements in an array, we've got elements in a vector, we've got elements in an array, we need to know row and column. We pass it sort of 2 addresses. Which row do I want to look in and which column do I want to look in to tell us exactly which cell. So the array 2D 1, 2 would be row 1, column 2, which would give us a value of 4. And sure enough, if I run this, it looks up and returns 4. So looking up, storing things, using 2-dimensional arrays is pretty straightforward. Now, R can have lots of dimensionality of arrays. In this book, the most we're ever going to use is 2 and 3-dimension arrays. So let's talk about 3-dimension arrays. So 3-dimension arrays, you set them up pretty much the same way. 2 arguments for the array command, what the numbers you want to put in it are, and what the dimensionality is. But now, instead of rows and columns, you've also got what I think of as slices, right? Think of like a Rubik's Cube. So you've got a slice, a 2-dimensional slice right next to you, and then a 2-dimensional slice behind it, and a 2-dimensional slice behind it. Now, if you try to look at a 3-dimensional object like this in a 2-dimensional manner, such as using the view command, sorry, I went too far there. R cheats, right? And what R does is it basically lays the slices down side by side. Now, it's up to you to realize sort of where the slicing happens. The fact that you told it you wanted 3 rows, 3 columns, and 3 slices, so it does the first set of 3 by 3 as the first slice. The second set of 3 by 3 is what I call the second slice. And the third set of 3 by 3 is what I call the third slice. So when you want to look up a number, so for instance, the array 3D, row 1, column 2, slice 3, you actually sort of need to look and figure out where the third slice is first. So first slice, second slice, okay, third slice. So third slice, row 1, column 2 is going to be a value of 22. And sure enough, when we ran the array 3D 1, 2, 3, that's what it gives us, 22. Now, matrices are a particular sort of type of array. By definition, a matrix only has 2 dimensions. So the command for creating it is a little bit special. You only have to pass it the elements you want in it and then the number of rows. You don't have to tell it the number of columns. Why? Because it only has rows and columns, and if you want to store 6 things in 2 rows, it has to work out that it has 3 columns. So you can look at it, and sure enough, it has 3 columns. Now, other than that, arrays or two-dimensional arrays and matrices work pretty much the same, with one significant difference. If you want to store things in a matrix, you can also use an argument by row equals true. See, when we go back and look at the arrays, it always stored column by column. So 1, 2, 3, it filled the first column, then 4, 5, 6, then 7, 8, 9. Even in the three-dimensional array, it filled the first slice, column by column, then the second slice, column by column, then the third slice, column by column. And by default, with the matrix, let's run the original matrix command again. By default with the matrix, it fills column by column by column. However, you can deviate from that by running this version right here. You can put in by row equals true. It stores the same numbers in the same number of rows and the same number of columns, but now it's going to store them across rows, 1, 2, 3, 4, 5, 6. Now, we're not really going to use matrices and rows much in the rest of this book or in the rest of the videos, but they're handy to have because they do help to speed certain things up. In a more advanced class, you would talk about the fact that if you have matrices or arrays of numbers, you can actually split them up and have multiple processors do things on different columns or rows at the same time. We'll talk about that in a limited manner in the next couple of chapters. Now, let's go on to sort of our next bigger storage location, lists. The nice thing about list is you can store different types of things in a list, and the command is simply list, right? So what this gives us, and again, you can use your square brackets to reference things, so the third thing in the list is going to be 1.5. Now, why is it having two pairs of squared brackets and then a single pair? Well, that's because a list behind the scenes, R doesn't like to store things that are of different types in a single vector. So it's really making a vector of vectors, if you will. And we'll see that lists are special classes and they're special types, but as far as we're concerned, it's like a list on a post-it note. You can put different types of things. Here we've put a character value, we've put an integer value, a double precision value, and a logical value, all in the same list. Now, we will see instances later on in the book where you might want to store some associated information, let's say about a person. You want to put their name, age, weight, height, and birthday, birth time, right? You could store all of that in a list and then refer to it using square brackets and the item of the list that you want to get back. Now, one of the things one of the commands for looking inside storage locations that we haven't really used yet because we haven't had things that were sort of complicated enough to want to, is the structure command, str. If you do structure on a list, for example, it will tell you, hey, there's 4 things in here. The first one is a character, the second one is integer, the third is numeric, and the fourth is logical. And this starts to give us an idea that for more complicated things, right, it's hard to see much information about what's in the list over here in the global environment. That's where you start wanting to use the structure command. And if you want to know more about the structure command, you can, remember, always ask for help on something by doing question mark, the name of a command, and then open and close parentheses. And particularly if it's a core command, it will go and show you usage. It gives you the optional arguments, but more importantly, it will also give you examples of usage that you can use. Now, let's clean up. Let's talk about our last special big type of data storage location called a data frame. We're going to create 3 vectors. We're going to take the numbers 10 down to 1, and you can do that, right? 10 colon 1 is going to be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Store those in X. Let's take the numbers from -4 to 5 and store those in Y. That's also 10 numbers, by the way, because there's a 0 in there. And then finally, let's take 10 names of sports and store them in Z. Now, a couple of comments here. First of all, with character values, you can't really use the shorthand of just specifying a range. You have to spell the 10 things out. Secondly, in almost all the scripts, you're going to find that I tend to be fairly good about using double quotes. However, that's not as strict a rule as the whole equal versus arrow thing for assignment. lots of programmers out there do like using single quotes. I prefer not to because I get mixed up, if you will, between a single quote and a parentheses or something along those lines. So I like to use double quotes just to make it very clear when I'm looking at my script that this was a character and it wasn't a parentheses and a possessive noun or something. But I wanted to show you that it is okay in most instances to use single quotes without any problems. So as we look at our global environment, we see that we've got three vectors, x, y, and z. Now, before, when we wanted to take elements and combine them into a vector, and what we did here with the z vector, we used the C command. If you want to take multiple vectors and combine them into what's called a data frame, which is as close to a table as we're going to get in R, or at least in core R, you use the DataFrame command. So if we run the DataFrame command, passing it vectors x, y, and z, and storing it into a memory location called the df, then the df winds up looking like this. It looks to a human's eye like a table when we look into it. You'll notice that it's added row numbers and it's added column headers, where the column headers were the names of the vectors, right? So the x vector, the x becomes the name of the first column in the df data frame, and so forth. Now, if you want to, you can look inside a data frame using that structure command. We see that there's three parts, and this is very similar to a list, right? But we see that there's three vectors inside there. There's an x vector that has integer values from 10 to 1, a y vector that's also integer, and a z vector. Now, you'll notice that it stored that as a factor. What's the difference between a factor and a character vector? Well, when you take a character vector and put it into a data frame, you're putting it into something like a table. R says, okay, is there more information other than the fact that it's a character that I can store? You may or may not have taken more advanced statistics, but in statistics, a lot of times you might want to group by commonality in a particular column. So a factor is one way to do that. The reason that R called that third vector a factor when it brought it in is it's saying, down the road, if you add more rows, and if you reuse any of these names that we already see, hockey, football, curling, right? So if you added more rows for any of those, there are statistic commands that would say, I want to find the average for all the rows that are hockey, or I want to find the regression separately for each level of factors, right? So here, as far as we're concerned, factor is the same thing as character. We're not going to be doing that type of statistical analysis, and frankly, we've got 10 different, quote, factors here. They're all different, right? We're not going to be grouping on the same sport anyplace. But R was just trying to help us out. So as far as you're concerned, think of factor as it's like characters, except there are ways to say, hey, group the elements that have the same values in that character vector, if you will. So ignore it for right now. Now, just as we saw with matrices and arrays and even lists, you can still use square brackets, right? You can still say, hey, I want to see what's in a particular location. But now it's going to be sort of which vector and which row in. So for instance, if I say the df 1, 2, I'm telling it, I want you to look in the first row, second column, which means the first row of the y vector, right? So the first row of the y vector is -4, and that's what it gives us back. Now, this is where the view command really comes in handy, because the view command goes through and shows us what's in the table, and it goes ahead and puts row numbers, and it goes ahead and puts column headers on there. Now, if you'll remember, way back at the beginning of the chapter, we ran a command called attributes. And we didn't really have any attributes of X. Well, when you start getting more complex data storage locations like data frames, it starts storing things for you, right? So this tells us, hey, we've got names, and those names are X, Y, and Z. So even though we see them when we run the view command, they're not sort of in the first row, they're in the 0th row, if you will, right? So if we did the average of the first vector, or the first column in our data frame, it wouldn't include X in that average. X is just a way to refer to that particular column. Now, and speaking of referring, the nice thing is when you have name metadata inside the attributes of a data frame, you can also use that to refer or to point to which part of a data frame you want to look at. So for instance, if I do the name, the df, $, and then I put the name of a column, it's going to give me back what's in that column. This is the same as saying I want to see the df square bracket 1. Right? It shows this to us in a little different manner because it assumes if you're using names for whatever reason you want to be succinct. So it shows you 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 splayed out across a row. But doing the df square bracket 1 would give us exactly the same stuff. It would just give it to us in a taller format, if you will. Now, the other thing is you can still use square brackets with names. But now if you use square brackets, you're using the $ name of the vector to indicate the column. So you only need one number inside the square brackets. You're telling it which element in that column or vector I want to see. So if I tell it I want to see the df $x square bracket 3, I'm saying I want column called X, named X, and then go down to the third element and tell me what that third element is. Now, and you're like, well, this is great, but X, Y, and Z are not very descriptive, right? I could just as well say vectors 1, 2, or 3. You could, but the nice thing about names is that you can edit them, right? So we're going to run this command here. This takes a vector that we create, a 3-element character vector with popularity, team strength, and sport. And then the names command on the left side of the assignment is taking that vector, not putting it inside the df, but putting it inside the metadata for the df in the portion called names. So when we do this, and then we look at what it creates, now we're going to see that if I run view, the column headings have more descriptive names than they did when we were just calling them X, Y, and Z. Likewise, if I want to go back and use descriptive names when I refer to elements, I can. We'll see that in just a second. The point is, when you've got data frames, you've got sort of two ways that you can refer to particular cells or particular elements in that data frame. You can still use square brackets, right? Now, if you just pass one number in a square bracket or a range of numbers, it assumes that you're giving it which vectors. I want to see the second and third columns, 2 through 3. I want to see the first and third columns. I want to see just the third column, right? You can also use names if you'd rather. So we can say I want to see the column called sport. Now, you can also pass names inside square brackets, and it does the same thing except it orients it vertically. The only thing you can't do is that if you have a column name that has a space in it and you try to run something like this, you're going to get an error. The reason is whether you put it inside square brackets or whether you put it after the $, team strength, because it has a space, R sees the df $team space, and it assumes you're done trying to name something. So the only caveat is that if you want to use names to refer to a vector or a column in a data frame, if that name happens to have a space in it, you got to put quotes around the name, right? So if I do the df $quote, double quote, team space strength, undouble quote, then I will get back the results of what's in the team strength vector. So that finishes the final video for Chapter 5 of Introduction to R for Business.